Section 3.7, page 2. So we're going to continue examples using L'Hospital's rule. So I'm asked to take the limit as x goes to infinity of the natural log of x over 3 plus x. So because it's to infinity, I could divide by the highest valued exponent in the denominator, but it kind of really gets me back to exactly where I was started. So we usually start with direct substitution. I'm going to plug infinity into the numerator. I'm going to plug infinity into the denominator, remembering that the limit as a function looks like this, that as I go along to infinity, even though it looks like it's flattening out, it is going to continue to gradually rise. So the limit is infinity, and infinity plus 3 is really just infinity. So I have an indeterminate limit. This allows me to use L'Hospital's. So I write the limit notation. I've got the h indicating I'm using L'Hospital's, and I take the derivative of the natural log of x, which is just 1 over x, the derivative of 3, which is 0, and the derivative of plus x, which is plus 1. So I really just have 1 over x divided by 1, which is just itself. So now I'm going to use direct substitution. Notice I still had the limit here, but now that I'm plugging infinity in, the word limit is gone, and 1 over infinity is 0. Now be careful, some people accidentally think that this is indeterminate because I have infinity, but notice I only have infinity in the denominator, not both the numerator and denominator. 0 is a fine answer, and it is not the same thing as 0 over 0. Next example, I'm evaluating the limit as x goes to 0 of something that I cannot factor, I cannot take a conjugate of, so we're always just going to start with that direct substitution, plugging in 0 wherever my x's appear. This is going to give me e to the 0 power, which is 1. I'm still going to have my minus 1, and 9 times 0 is 0. So I really just have 1 minus 1 in the numerator. Any 0 to any power is just 0, and so I've got my indeterminate form. I want to now take L'Hospital's rule to allow me to take the same limit, where I'm going to take e to the 9x, and the derivative is to copy the question, take the natural log of the base, but that's 1 in this case, and the derivative of the exponent. The derivative of minus 1 is minus 0. I'm sure you don't write anything, but I don't want it to look like terms disappeared. And minus 9x has a derivative of just minus 9. The derivative of x squared is 2x. So remember, I still had the limit. Because I was kind of showing where everything was coming from, I'm going to clean this up and write this all right here. You might actually only write the piece in the box. But now that I have limit of something I can plug 0 into, I will plug 0 into all the variables, giving me, this is going to go ahead and be 1. So I really just have 9 minus 9, which is 0. 2 times 0 is 0. Now, this didn't help me, but because it's 0 over 0 indeterminate form, I'm just going to go ahead and use L'Hospital's again. So I'm going to go back to that simplified form I had. I'm going to put an H to inform you that I'm doing L'Hospital's. I'm keeping the exact same limit, and I'm going to have 9 times the derivative of e to the x, where I copy the question. We already said the natural log of the base is 1, and the derivative of the numerator is 9. The derivative of minus 9 was minus 0. And the derivative of 2x is just 2, but I was kind of writing that x turned into 1. So ultimately, I have 81 times e to the 9x all over 2. Still have my limit, but now I'm going to go ahead and plug 0 in for x, so my limit is gone. This gives me e to the 0, and anything to the 0 is just 1. So I really have 81 over 2. Now there's another type of indeterminate that you're going to find, which is called product indeterminate. Specifically, you have 0 times either positive or negative infinity. Now here's the tricky part. L'Hopital's required an indeterminate form of 0 over 0 or infinity over infinity. But what we're going to do is we're going to turn a product into a fraction. So if I had f times g, I could rewrite this as f all over the fraction 1 divided by g, or g all over the fraction 1 divided by f. So notice if you have a fractional term function in the denominator, then it's the numerator divided by the denominator. But when we divide by fractions, we take the reciprocal. So I really just have, well, I don't want an arrow there. I have f over 1, and anything over 1 is just itself. So if we're taking the limit of a product and we end up with product indeterminate, we're going to need to rewrite the function, the problem, having a fractional denominator that's underneath 1. Now, the one you're going to choose is the one that makes the problem easier, and it's not always the one I choose first, so sometimes you might have to retry something. Here's an example worked out. I'm asked to take the limit as x goes to 0 from the right side of sine of x and natural log of x. Now, obviously, sine can be evaluated at 0. Technically, the natural log of x does not exist at 0. If you remember, this is our shape. And so we have a vertical asymptote at 0, but we do have a limit that tends towards negative infinity when we come from the right side. So first, as always, I check by plugging in the value we're evaluating the limit at. That was so hard to say. So all I've done is copied the question down here. I'm essentially going to go ahead and plug 0 in. We can still think 0 for a minute, right? So I know the sign of 0 is 0. Now, technically, the limit of 0 doesn't exist, but I'm really thinking the limit of 0.000 and I know that that is going down or tends towards negative infinity. This is product indeterminate, so I'm allowed to use L'Hopital's. But before I can use L'Hopital's, I actually need to rewrite the question and confirm that I can use L'Hopital's. So I've taken this original question that we have, and usually it's best if you have a limit that I'm going to leave the limit on top. And instead of just putting the sign in the denominator, it's the denominator of a denominator is one way to phrase it. So now I've got limit in front, but limit's gone because I'm plugging 0 into both variables. We already discussed that the natural log of 0 essentially tends towards, I should say negative infinity there. Sorry, I just caught that. And 1 over the sine of 0 is 1 over 0, which doesn't exist. But remember, we're not actually using 0. We're using 0 from the right. And so it's really like 1 over 0.000, which actually is infinity. So I have negative infinity over positive infinity, but it still satisfies L'Hopital's. So I have taken my rewritten question, but before I use L'Hopital's, because I need to take a derivative of the denominator, it's usually going to be best to write it as a negative 1 exponent. Remember, this does not mean inverse sine. If it was over here, which it could be when we use exponents, but we won't when it comes to the negative 1. So I now have a function. I'm ready to apply L'Hopital's rule, where I still have the limit. The derivative of the natural log of x, by definition, is 1 over x. This is going to require a chain rule derivative where the negative 1 comes out front. The question stays identical, but we subtract 1 from the exponent to get a negative 2. And then I take the derivative of the inside, which in our case is cosine x. Okay, so I've got this 1 over x. Now, notice this sine to the negative 2 would go underneath here. But remember, when we're dividing by this, we're multiplying by the reciprocal. So the cosine would go to the denominator, and the negative 2 piece goes to the numerator. The negative sign can be either spot. Because I have sine squared, I went ahead and wrote the sine times itself twice, because hopefully you can see the x that was in the denominator can be paired with the sign in the numerator to use the sine property where this equals 1. Keep in mind, we probably should have written, you know, the limit of the sine of x all over x times the limit of, you know, we've got the sine of x all over the cosine of x, but I kind of shortened that up a bit. So I've used the sine property to just have my negative sign in the numerator, the cosine in the denominator, and now I have a simplified limit that I can evaluate. Limit goes away because I'm plugging 0 into both variable spots, where I know the sine of 0 is 0. I kept the negative sign so it doesn't look like it disappeared, but 0 is neither positive nor negative. Cosine of 0 is 1, and so 0 divided by anything is just 0. It might have been tempting to enter the tangent here, and really the tangent of 0 is 0, but in case you weren't familiar with that or it doesn't come as quickly to you, keeping it as sine and cosine is completely fine.